Well, in the last class you have seen that if you apply the Kirchhoff's laws in a raw way, which means simply application of the mesh current and the node voltage methods, then things have to be attacked ad hoc. The other problem is that if there is some redundant capacitance or redundant inductance, redundant means where the state variables associated with those capacitances or inductances are not really free. They are, because of the specific connection, dependent on the voltage sources, the other capacitances. So, the voltages become related, and so they are not free to choose any value. In that case, they do not become state variables. And in case of such circuits where you have this kind of atypical problems, the application of that method becomes somewhat difficult. The third problem is that the mesh current method, after all, is applicable only to planar circuits, right. If there is a circuit something like this, you have one then you have problem. It will not be easy for you to identify what the meshes are. It is not a planar circuit. So, in those cases we cannot apply the method, and that is why for electrical circuits it is necessary to have some kind of a general easy to use method with which we can derive the differential equations for even very complicated circuits, and that is provided by the graph theory. So, today we will in the main deal with this graph theory approach of deriving the differential equations. Now, in this approach, whenever you have a circuit consisting of inductances, capacitances, resistances, all these are represented simply by branches. So, this will represent a branch, this will represent a branch, this will represent a branch, and so on and so forth. Okay. So, there will be all these are represented by branches, and the branches are connected through nodes. So, if you have the circuit that we did yesterday, if you have a circuit like this, here it was the inductance, here was a capacitance, a resistor here, and a capacitor here. Then this circuit will be represented by the graph. The graph will be, how many nodes are there? 1, 2, 3, 4, which we denoted as 0, 1, 2, 3. Here also it will be 1, 2, 3, 0. But in between we will connect simply by lines. And there is another branch, that is it. So, when we draw the graph corresponding to a circuit, we initially forget about what are the contents of its branch. Each branch is just a line. So, that is the graph corresponding to this circuit. Similarly, you can easily imagine that you can draw graphs for any given circuit. Now, in this circuit, in this graph, I can see there are 4 nodes and there are 1, 2, 3, 4, 5, 6 branches. In the next step, we need to identify them. So, the nodes need to be identified, and we will do similar way by means of numbers 0, 1, 2, 3, and branches will have to be identified. We will do so by means of letters, say A, B, C, D, E, and F. So, when I say now I am talking about the branch C, you immediately know that this is the branch I am talking about. Okay. So, it will be easy for us to work with these branches. Now, obviously, the branches carry current and there would be voltages between the nodes, right. And this graph as yet does not tell us what are the directions of the currents or the positivity or the negativity of the voltages. So, we will need to assign some kind of a direction, and that direction again would mean that say if I give the direction like this, what does it mean? It only means that this is the direction of current which I am considering as positive. So, if the current actually flows in the opposite direction, no problem, it will only appear as a negative value. So, my positive direction is like this. So, this way we will direct all the graphs. So, suppose I direct it like this, like that, these are all arbitrary, I just gave. So, whenever I have given the directions, it is called a directed graph, or in some books you will also find digraph. You might ask, okay, I have given the direction of the currents, what about the voltages? Notice that the moment you give the direction of the currents, the positivity and the negativity of the voltages immediately become defined. For example, in this branch the current is given this direction as positive, which would mean, which would imply that the node 1 is at higher potential than node 3. So, the assignment of the direction in the branch essentially immediately also assigns some direction of the voltages, clear. So, the first step is to define this kind of graph. The next step is, notice the concept, you cannot cut this graph. Suppose you have taken a pair of scissors and you simply cut. In how many possible ways can you cut it? In many ways. For example, you can cut it like this. You can cut it like this. Right? You can cut it like this. Cut it in such a way that the graph becomes divided into two disjointed parts. So, you cut it so that the graph becomes divided into two disjointed parts. These are called cut sets. These are called cut sets. So, how many different ways can you think of? Just take this graph and try to think how many different ways. You will find you can cut it in very many different ways. They are all possible cut sets. That is one concept, the cut set. The other concept is loop, which is the same as what you have already learnt regarding the loops of this circuit. So, you can easily identify there are loops like this, right. Now, on the basis of this concept, we will redefine the Kirchhoff's laws. What does the Kirchhoff's current law say? Current law, earlier when we wrote the Kirchhoff's current law, then we said that in each node all the currents entering or exiting sum to 0, right. Now, we will restate it by saying that at any cut set, all the currents going from one side to the other, one subgraph to the other subgraph, sum to 0. So, it is a higher level of definition of the Kirchhoff's current law is understood. For example, here this particular thing, it is not really related to any particular node, this one, but yet we can say that the IF plus ID plus IC plus IA is equal to 0, right. So, but this is related to one particular node because it is isolating only one node. Here again we can write in the old way I A plus I B plus I F equal to 0. So, this is something that we knew already, but this is something that we have learnt now, that it is also related to cut sets, not only nodes. Okay. So, the Kirchhoff's current law KCL and the KVL would state like this: the KCL is related to cut sets and KVL related to loops. So, in all the loops, the VA plus VC plus VB equal to 0, but notice here, while you do it on the loops, you will have to traverse either the anti-clockwise direction or the clockwise direction. For example, if I want to write the KVL equation in 0, 1, 2, this loop, I start from here, VA minus VC minus VB equal to 0. Okay. If I say do it on this loop, this is also a loop, VA minus VC plus VD minus VF equal to 0. Fine. So, that is how we will do it on the loops, and while we do on the cut sets, we will say that for every cut set, for example, for this one, it is, suppose the currents entering this cut set, this particular subgraph is positive, then IE plus ID plus IF equal to 0. So, this says that the sum over loop, the V n equal to 0, and this says sum over cut set I n equal to 0. Okay. Fine. So, we are one step higher than where we were earlier, but now we need to define something more. So, there are, you can easily see that there are various ways of defining the cut sets, and there are a few some number of loops. Now, we had started by saying that the basic step in the obtaining of the differential equations relate to the Kirchhoff's laws, and the Kirchhoff's laws are applicable to cut sets and loops, and you can see there are many loops here, and also there are many cut sets. So, out of that, which one would be most convenient for us to use? That is the key issue. Now, in doing so, let us define one more concept, that is called a tree. So, let us redraw this graph. It was one node here, one node here, one node here, connected to another node here, and a third one. So, that is how my shape was. It was A, B, C, D, E, F, 1, 2, 3, 0. Now, tree is the maximal number of branches that you can connect without forming a loop. The tree is the So, from this how many different trees can you identify? Let us see. In order to do that, start from any branch, any particular node and go along a branch. So, we can start from here A1, go along this, go along this. If we go along that, we complete a loop, we cannot do that. Then we can come back along this, but if we do this, it will be completed. If we do that, it will be completed. So, that completes a graph. So, 1, 2, 3, 0, that is a one possible graph, one possible tree, yes. Now, let us start from another direction, let us start this way. So, first, second, third, can we take any more? This does not allow, this does not allow. So, 1, 2, 3, 0, another tree. Let us start from that direction. Then I can come this way or you can come this way, let us come this way. Then I cannot go there, I have to come here, I cannot do any more. So, these are all the possible trees. You can easily see there can be more. What remains if you have connected a tree? The rest of the things remain. For example, if I draw in a different color, this is what was remaining, this is what was remaining and this is what was remaining. So, the blue ones connect the tree and the red ones are the co-tree. So, the things that remain after you have identified the tree, they are the branches of the co-tree. So, these are the co-tree and these are the branches of the tree. So, here what would be co-tree? This, this and that. Here this, this and that. Okay. So, these are the tree branches and these are the co-tree branches. You might notice one interesting thing, even though we tried to connect the tree in various possible ways, always we ended up in 3 branches as the number of branches in the tree. Notice, and you try to connect in any possible way this particular thing, it will always land up in 3. That is one interesting thing. For planar graphs, that always happens. It will always, the tree number of branches in a tree will be the same. Yes. Fine. So, we have identified the tree and the co-tree, and we have learned to identify the tree and the co-tree in any graph. But still we have the problem that we can connect in many possible ways. Many possible ways we can connect the tree, and out of that some must be giving us the advantage, but let us see. Now, the question is, what should we choose as our state variables? We know that the voltage across a capacitor is a logical choice of a state variable. The current through an inductor is a logical choice for a state variable. But then we have also seen that not always. There can be some voltages across capacitor that are not independent, some currents across the inductors that are not independent. So, we need to choose properly. Okay. Now, we have identified the trees and the co-trees. So, let us go to the next step. How to choose the state variables? Now, you can now apply cut sets on this. Let us do it in a different color. We can apply a cut set like this, we can apply a cut set like that, and so on and so forth. Now, there is a specific definition. If I can identify a cut set that cuts only one tree branch, then it is a basic cut set. So, here we have cut it in such a way that it cuts only one tree branch. So, it is a basic cut set, while this is not. So, this is a basic cut set. In this case, can you identify? This cutting will not be a basic cut set, this cutting will be, this cutting also will be. In this case, can you identify? Even this cut set will be, right? It is a basic cut set. So, these are the basic cut set. Similarly, in this case, this will be a basic cut set, that will be a basic cut set, this not, is there any other? No. So, these are the basic cut sets. So, basic cut sets are one that contains only one tree branch. Similarly, the basic loop is one that contains only one co-tree branch. So, let us see, let us try with this one. We have done it like this. Can we identify the loops? The basic loop would be one which contains only one co-tree branch, right? 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 All these are then basic loops. Clear? So, this is also basic loop. Start from here. It is, oh no, this is. Sorry, I made a mistake. Let us do it correctly. This, and this are the. So, only one co-tree branch. So, red one is a co-tree branch. So, this is one. Is there any other? Not this? Yes. Any other? This. Yes. So, these are the basic loops, the loops that contain only one co-tree branch. So, this is the basic loop. So, we have introduced the concept of the tree, the co-tree, the loop, the basic cut set and the basic loop. There can be very many cut sets, but out of that some will be the basic cut sets. There can be very many loops, out of that some will be the basic loops, and we will concentrate only on the basic loops. There is a reason for that. Okay, now the state variables. We will choose, as I told you, the capacitor voltages are state variables. We will choose only those capacitor voltages as state variables that form the branches of a basic cut set. And in case of inductors, we will choose, inductor means inductor current will be a state variable, those inductor currents that form the part of the basic loop. Let us see how to proceed with that. Now, let us proceed with this. Now, this way also we are not very happy, because what we said, we will choose those branches that are forming the basic cut sets, but you can see there are various ways of forming the basic cut set. Out of that, which one do we choose? Now, there is a specific choice to that. We will choose that particular thing in some order of priority. We will see out of the various possible trees, we will choose that particular tree which has the following properties: tree with the following properties, following priorities. First priority is it should include all the voltage sources. So, out of various possible trees, we will choose only that tree that includes the voltage sources. Second, it should include a maximum of capacitors. Three, it should include a maximum number of resistors. Finally, when we still cannot complete a tree, then we will say that it may then include to complete a tree. Okay. Let us see. The point is that in any given circuit, I can draw a tree in various possible ways, and for every tree I can draw many ways to draw the cut sets. I can have many ways to draw the basic loops. So, these are giving us a too many options. We do not like that. So, we need to restrict our options so that we can have a very algorithmic procedure to write down the differential equations. So, out of all possible trees, we will choose the one that satisfies these requirements. Let us see. What was our original circuit? It was like this. We said that there are various ways of drawing the trees. The one that we want should be first including all the sources. So, they should include this. So, out of the possible trees, you can see only this one includes that, right. Can you see? It is this branch, it should include, only this one includes that. Let us see. The next point is that it should include a maximum number of capacitors. Let us see. There was a capacitor here and there was a capacitor there. So, which one will that do? This one does not do that, because this does not contain that capacitor. Which one? No, it does not. This does not include this capacitor. So, we need to do it some other way. This one does not, because this was the branch with the source, it is not included. So, this is out, this is out, this is also out. So, these are not the right choices of the trees. So, let us start doing it again from here. Look at the circuit. I will draw the circuit and then start off. Here was, I will draw a little fast, so that we can quickly do it. Here there was a resistor, here there was a resistor, and here there was a capacitor. Now, it is, we have to include this. So, include this. We have to include the capacitor, we have to include this capacitor. That is it. The moment we try to include, the next point was it should include the maximum number of resistors. The moment you try to do that, the loop is closed and therefore, it does not remain a tree. Here also the same problem, and we do not need any inductor to complete the tree. So, that out of the all possible trees is a very special tree which we will use. It is called a standard tree. Right. So, what are the core tree branches? These are the core tree branches. Is it visible as two different colors? Okay. Then the tree and the core tree we have identified. Now, we will say that we will take those as our variables that are related to the tree and the core tree. So, we will write that if since the capacitors are included in the tree, therefore, the state variables will be the capacitor voltages that are included in the tree. The way we have drawn it, the inductors will be in the core tree. So, the state variables will be those inductor currents that are included in the core tree. Fine. So, we have identified the state variables. What are they? State variables are, tree capacitors and core tree inductors. These are all related to the standard tree, not just any tree. Fine. So, we have made a choice of what we will call our state variables. Notice that in those cases where there is some dependent capacitance or dependent inductance, immediately that will go out of the number of capacitances that we choose, because they will not form branches of the standard tree. We will see, we will do that by examples. Now, when we try to obtain the equations, differential equations, what we will do? First, we will say that okay, now I am trying to obtain the state variable equation for this particular capacitor branch. I am now trying to obtain for this particular inductor branch. Good. If the variable is a capacitor voltage, if the variable capacitor voltage, obviously that capacitor will be part of the standard tree. So, identify a basic cassette containing that capacitor. Then write KCL, that is it. Second point, if the variable is an inductor current identify with that inductor. Then write clear. So, we are not going on writing the KCL and KVL equations for all possible loops, trees, branches, no. We are just doing it for the specific cases. What is it? If we are trying to write down the equation for the capacitor voltage, we will identify the basic cut set, we will identify the basic cut set, and then we will write the KCL for that cut set, that is it. So, let us illustrate. We had this circuit, we had this circuit and we had this as the standard tree. Let us give them names 1, 2, 3, 0, and then we said A, B, C, D, E, F. We had also given directions like this. Fine. So, that is our starting point. We had identified this as the standard tree and the other one as a co-tree. So, now we have to identify the state variables. What are the state variables? State variables would be the capacitor voltages that are parts of the standard tree, which are the, this was our C1, this was our C2, L, R1, R2, E. Obviously, C1 voltage VC1 is one state variable because it is a part of the standard tree. This is also a part of the standard tree. So, VC2 another state variable, VC1 and VC2. Okay. And the inductor current, that is part of the co-tree. So, inductor, that is part of the co-tree, it is IL. Fine. So, now let me, first your job is to identify, suppose you are obtaining the equation for VC1 here, identify what? A cut set, a basic cut set that contains this branch. Can you identify? Here, that is the basic cut set. Immediately we can write down the KCL equation as, let me display it here and write it. It is, notice the arrows, VB, IB minus IC minus ID equal to 0, right. Notice plus minus minus. So, for VC1 we are writing it IB minus IC minus ID is equal to 0. So, that is the starting point. We can easily identify that IC is C dV dt, clear. So, immediately that gives. So, we will write IB minus C1 dVC1 dt minus ID is equal to 0. Yes, IB is a state variable, here is IL, right, which is state variable. So, we are happy, we will write it back, write it down here, but first let us take this one to the left hand side and the rest in the right hand side, the way we write differential equations. So, d Vc1 dt is equal to, it is 1 by C1. Now, I can write it as IL. This should all be small letters because these are variables. Sorry, capital letters imply fixed values. IL minus ID. Okay, what is ID? ID, current to D. Here is a resistance sitting. So, it is there is a resistance sitting here. So, how will I write it? Yes. So, we can write it as, or V2 minus V3, or voltage in D, VD, we can also write that. VD by R1. Okay. Now, we do not yet know VD. Yeah. We do not yet know VD. So, VD is not a state variable. So, we need to do something about it. VD, where do we get it from? VD, V, that should be obtained from a loop. Okay. Cut sets yield the currents, and then this will be obtained from the basic loop that contains this. Okay. So, what is the basic loop that contains this branch? 2310, yes, this. So, write down the KVL equation in this loop. You get VD is equal to, this equal to minus VF, no, I will not write equal to, then it will be a problem. Start from here, minus VF plus VA plus minus VC, right. We are going around. Start from here, VD minus VF plus VA minus VC equal to 0. That gives VD is equal to VF, yes, that is VC2, VA, which is E, it has gone to this side, and VC plus. So, you know all these, the right hand side is are the other state variables. So, you simply substitute it here, you get the equation. Clear? Okay. Here is a question. VA is E or minus E? Good question. You have normally this as the polarity of this, which means that this is at a higher polarity than this, which means this is okay. That means in that case the current will flow through like this. Okay. So, accordingly we have taken. Fine. So, substitute this, we have got. Now, for VC2, which cut set should we take? C2 is here. We have to write that basic cut set that contains only this. What is that? This. Fine. Write down the equation. It is IF plus ID plus IE equal to 0. IF plus ID plus IE equal to 0. Okay. Out of this, which one do I need to know? This is C dV dt. Okay. So, C2 dVC2 dt is this, is equal to minus ID. ID is same thing, we have already done it. So, we can simply substitute. So, ID is Vd by R1 and Vd we can substitute, we know what it is. This one IE is this one. IE is VE by R2. We already know this, but we need to know this. For this again we need to know this voltage, and for this again we need to identify this particular voltage we need to know, and this voltage will be obtainable from the basic loop that contains this branch. What is the basic loop? Can you identify? No? 0310, yes. Here it is. So, you write down the equation for that. Start from here. VE minus VF plus VA, fine. So, VE I want to find out, VE is equal to VF is VC2 plus, it will come to this side, minus VA is E. Okay. So, you just substitute it here, you get it. Finally, the state variable is for IL. This is obtainable from, what did I say? The basic loop equation that contains this branch. Where is the basic loop that contains this IL? Yes, this. So, write down the KVL equation in this. So, it will be, start from here, VB plus VC minus VA is equal to 0, right. Notice VB plus VC minus VA, because the arrow is opposite, equal to 0. Now, your VB is L DIL dt. So, we have got one thing, plus VC is already known, VC1, VC is VC1 minus VA is E, equal to 0. So, DIL dt is equal to minus 1 by L VC1 plus 1 by L E. That is the third equation. Clear? So, once you identify the standard tree, the rest of the things become pretty simple. Let us quickly do one problem. It will also be useful for circuits that are not planar, but here we have used a circuit that is planar.
Yeah, but the thing is that if the circuit is non-planar, the graph itself will be non-planar.
Yeah, yes. Yes, it will be non-planar. So what?
Determining the cycles and all this is difficult.
No, here we are not identifying the meshes. Here we are identifying any closed loop, which even if it is non-planar we can identify. Here the idea is not to identify mesh. Mesh is planar, but the loops that satisfy certain property, we can still identify that. Okay, let us do this problem. We have here you start doing, because in this class we do not have much time left. Can you do it? By other methods it will be extremely difficult, by any other method. By this method it will be rather simple. So, it is L1, L2, C1, C2, R. Do it. First, quickly draw the graph. The graph will be so the graph will contain these as the branches. Now, let us try to directly identify the basic tree, the standard tree. Standard tree should contain this thing. So, it will contain this branch. Standard tree should contain these, yes, right. Now, you notice that if you close any of the other things, it will complete the loop, and therefore, this is the standard tree. Okay. Once we have identified, quickly give the numbers 0, 1, 2, 3. So, the co-tree will be good. What are the state variables? The capacitor voltages associated with 3 capacitors. Okay. So, this is a tree capacitor, this is a tree capacitor. The state variable will be VC1, VC2, and the co-tree inductors. So, IL1 and IL2, all of them. No problem. Let me just illustrate one equation, just one. Yeah. Suppose we want to find out this capacitor voltage for VC1. We have to identify the cut set that contains the C1 branch. It is simple. Right. So, immediately you write down the equation. Write down the equation. We have to give the yeah, ABCDs. Yes. So, let us say A, B, C, D, E and F. Fine. So, now we can directly write directions. Yes, give directions. Obviously, they are arbitrary. So, let me give directions. And this. So, IB plus IF minus IC is equal to 0, first equation. Out of that, IB is C1 dVC1 dt plus IF is what? IF is VF by R, that is enough, and IC is also state variable minus IL1. Good. So, we can take this one to the left hand side and write dVC1 dt is equal to 1 by C1 minus R. Now, we have to write VF. We will find what VF is, but let me write it now, plus 1 by C1 IL1 L1. Vf is needed. Vf is a voltage which will have to be obtained from a basic loop. So, what is the basic loop containing Vf? 0, 3, 0, 2, 3, 1, 0. Yes. So, this is the loop that contains Vf. So, write down the equation for that. Let us start from here. So, it is Vf minus Vd minus Va minus Vb equal to 0, fine. So, Vf is equal to Vd, yes, Vc2 plus Va is, yes, opposite. So, minus E, and Vb is okay, substitute, you got it. So, this is how the equations are to